Are you ready to go? Or? Yeah. Okay. Hey, good morning, everyone. It's been an interesting conference. We're glad to be here today. We are both from DataPelago. I am John Janakiraman. I lead engineering for DataPelago.
I'm Satya Villa, and I'm a technical fellow at DataPelago.
So we're going to switch in the middle. We're going to switch in the middle. Okay. I'll start on the first few slides, and we'll proceed with Lakshmi after that. Okay. DataPelago, we is a startup based in Mountain View. About 5 years ago, we realized something that is kind of common knowledge to everyone here, that data and AI are kind of driving forces in making technology advance. They're almost dictating everything today. Closely related to that is that there is a surge of innovation in accelerated computing hardware, whether it's in GPUs or FPGAs or TPUs and things like that. So that is what we set out to mine and build a data processing acceleration engine that will work for any processing platform, things like Spark, and be able to process diverse data on any infrastructure. So that was the genesis of the company. What we built is a core technology called DataPelago Nucleus. And as the diagram shows, that is intended to unify both relational data processing, query processing, traditional query processing, and also model-based processing, where you can use machine learning models to drive processing itself. So that enables you to work on diverse data, whether it's tabular data or JSON type semi-structured data, or PDF files and so forth, on whatever hardware is available. If you have just CPUs, or if you have CPUs and GPUs, the cloud providers also provide other computing elements like FPGAs, and things may evolve in the future. We wanted to enable all of those things for our customers to be able to do the data and AI processing. So that's DataPelago Nucleus. We'll talk a little bit more about it. Our primary product is DataPelago Accelerator for Spark. And it is available in the cloud, in GCP, and in AWS. And we have customers who are actively running DPAs for serving their production workloads. Okay. DataPelago Nucleus, if you are a computer architect, you need to define systems with very clean language interfaces, clean hardware interfaces, both for composability, which the community here knows very well, for also to be able to be future ready for future engines. Everyone knows there is a rapid evolution in the hardware that is available. I mean, from NVIDIA, from other players. Data is becoming richer. All kinds of data are being processed. And we're talking about Spark, and then Flink, and then Axiom. So the variety of programming models that are being applied is not going to stop. The data is going to become richer, and the computing elements that are available are going to become richer. So we need to build a product to be a sustainable product for the long term. So what we have is an architecture that drives that. So at the top level, we have basically an intermediate representation, which provides a unified representation for computing models, whether you express it through Python or SQL or through Spark or Flink or Trino or Presto. We want to be able to absorb all of those things in a uniform way. That's at the top layer. And at the bottom layer, we want to have a hardware abstraction layer that makes it possible to run on hardware as it evolves. We don't want to change the entire stack just because we have a new generation of GPU in itself, right? So that is captured in the PDU accelerator interface. So in between these two things are the layers of DataPelago Nucleus. There are basically three key components. I'll talk to them in the next slide. At the application layer, it's the data app, and that generates these IRs. And then at the bottom layer, there's a data VM. VM stands for virtual machine, and that is really the one that is at the bottommost layer. And in between, you have the OS kind of layer, which is the data OS. What I want to point out is that since this is Velox, this execution engine, we saw yesterday, Masha talked about Axiom, a planner engine in C++. So we also believe that to be successful, our platform needs to combine the execution layer and the planner layer. So DataPelago Nucleus encompasses both of them so that we can actually bridge the application to the hardware in an ideal way. So that's the overall architecture. So the components, as we described, right, they are data VM, starting from the bottom, data OS at the next, and then the data app layer. The data VM is very sophisticated. We have a lot of pride in building like the first industry's first domain-specific data processing virtual machine. So it basically is a virtual machine like you would think of as JVM, or a Java virtual machine, or an x86 machine, or a ESX virtual machine. But it has languages that describe data processing. The data processing could be, find, personal identifiable information in some PDF file, or it could be, do a join, right? You can describe verbs like those things as part of that language, and that is all that we code to from the top layer, and that language is basically serviced by a device called the PDU. And that PDU is the one that everything, all the layers of translation, compilation, and interpretation about that, it codes to that. That basically allows us to insulate every layer above from the device specific itself. And then we realize this PDU on these various hardware elements, whether it's a SIMD CPU or it's a GPU, we realize on all of those things. Today we have data VM implemented on x86 SIMD machines, NVIDIA GPUs, Xilinx FPGAs. We have the entire stack running on all of them. So we can actually accelerate all of these Python and SQL platforms on all of these platforms. But it's built to be able to, when we have TPUs or other new devices, we can actually enable those things as well. The layer below that is the data OS layer, which has two functions. One, it's basically the thing that converts or compiles the intermediate representation that describes the application logic to the language that I described as the instruction set architecture. So that is one core function of it. And there's a lot of intelligence in it, which we'll touch on some of that when we talk about the planner. Just as you can figure out various ways to do joins, you can figure out what are the most optimal ways to execute a particular program using these instructions, just as a compiler does. It may be that there is no GPU, or it may be there are two GPUs, or it may be that there's only two CPUs. So all of those things are relevant in generating this compiled program. The other core capability of data VM is the resource management itself. How many operators are being currently executed, how much memory is available, right? So all of those things go into resource management decisions that Data OS takes at runtime. The last one is the data app. In the context of Spark and Trino and Flink, data app is a plugin. This is the one that makes our platform easy to interface to existing platforms. This is similar to how Gluten interfaces to Spark. And it can consume these Spark plans or Trino plans and convert them into this intermediate representation that is defined by DataPelago Nucleus and is used by DataPelago Nucleus. While in the context of Spark, we don't need to do all of the planning. Spark does its own planning. DataPelago Nucleus also includes a full-fledged planner that can actually take the Python program or the SQL program and actually generate IR from scratch. So anyway, that's an overall component view of DataPelago Nucleus. So for today's talk, we want to kind of highlight two of the key technical elements. One is the data VM, specifically its realization on GPU. As I mentioned, this is one of our crown jewels. Lakshmi will talk about it. And then following that, I'll come back and talk about some of the planner-related smart acceleration.
Thank you, John. So in the last year's session, we introduced this data VM and also explained why we think this is the better way of offloading the general purpose computation onto the accelerators. So you can see on the left side, it's most CPU-centric program. In a typical CPU, you usually have an ALU, a register file, and a control unit. ALU is the workhorse there. And all the software virtual machines typically mimic what the CPU does. If you look at the JVM instructions, it's mostly add, load, store, add, subtract, shift, and so on. Whereas on the right side, if you look at the data VM program, it's more high level. You can see the parse instruction, select instruction, building a hash table, and so on, right? So we covered these in the last session. So today, I'd like to shed some light on why we believe this is a better way of offloading general purpose computation onto the accelerators. So if you look at even though this slide shows that x86 CPU is not really an accelerator, but if you get into the details, most of the CPUs have, for example, AES instructions. That AES is typically done in less than 10 clocks. So it is in a way accelerator CPU. So if you go to the very bottom and see what a general purpose CPU looks like without any accelerators, right? So this is one such example. A chap called Stephen Dolan, he proved almost 10 years ago that a move instruction as it is defined in the x86 CPU is actually Turing complete. So which a move, as you know, is used to move data across registers to memory, and memory to register, and so on. And another chap called Chris Domes, he actually implemented a C compiler just for that machine, which means if you imagine a CPU with just move instruction, and then you can actually execute all your programs on that, just one instruction. So let's call that move CPU, just for sake of conversation. And let's contrast it with the x86 CPU, right? So on the middle, you will see a simple Fibonacci program written in C. On the left-hand side, you compile it, and then you got the right answer at 9. And then if you look at the object dump, I highlighted the instructions, the top-down. You see a comparison with 0, comparison with 1. Just like in the C program, there's n is equal to n is equal to 1, followed by a call to the Fibonacci recursive call, and then addition. So you can make sense of what is on the left-hand side. On the right-hand side, it's the same move compiler. You compile it down. If you look at the object dump, it's just full of move instructions. But you still get the right answer. Right? So now, good luck finding where the comparison is and where the jump is and so on. But nonetheless, it's a very general purpose computer. It has no acceleration, just one instruction, but you can compile any program down to this CPU. So now what's the catch here? If not, if it can do anything, then why not build a CPU with just move instructions? So the same guy who implemented the C compiler compiled this Doom video game. On the left side, you can see it can do 60 plus frames per second, which is comfortable for playing a video game. On the right-hand side, the same Doom binary compiled using just the move instructions, it actually renders 1 frame every 7 hours. So you can see the difference. Even though the x86 CPU instruction set looks very primitive, it's actually orders of magnitude faster than the most general purpose computer, right? So if you go along the same vector, in the same silicon, you can see silicon implementations that are orders of magnitude faster than a general purpose x86 CPU. For example, if you look at switching ASIC in a top of the rack switch, for example, which typically has 40 servers with 100 gig linkage, and they all go to the top of the X server, and that can do 40 times 100 years, 4 terabit per second switching. So if you put a general purpose CPU inside in that, and then say, okay, go switch 4 terabit, it cannot, right? So there is a very special purpose chips designed in multiple generations to get to that 4 terabit per second. So if you kind of draw a system design 101 chart, where the most general processor on the right-hand side and the less general on the left-hand side, less performant on the bottom and the most performant on the right. CPU move, of course, our move CPU is the worst one. It's very general, but it's not useful. 7 hours per, one frame every 7 hours, probably a human can draw that whole frame by hand. So whereas CPUs or GPUs are a lot faster, but they won't give you the higher maximum throughput. And most of the accelerator vendors are on the left top. The switching, it's not really programmable, but it is really fast. So for example, Intel's QAT accelerator, it does compression encryption. It does really fast, but it doesn't do anything other than those, right? So in this setting, where do we want to be? So we want to be on the top of the right-hand quadrant, right? So we wanted the most general purpose processing element that is high performant. Now, how do we get that? For practical reasons, we implemented it in 2 formats. One is a virtual machine, which we call the data VM, that it's most general, but it also, it's Turing complete, but it also has instructions at a higher level than a general purpose CPU. Now, there is another component to it, which we call PD, which is essentially a hardware hardware specification that describes how to interface with the different types of hardware accelerators, and also what kind of hardware accelerators make sense and how to implement those, right? So that's what essentially the data VM is. This is the thinking behind our virtual machine. So with that in mind, as John said, so there's a PDU layer at the bottom, and you can take that hardware abstraction and implement it in anywhere. So we started with an FPGA. We took that, we had some learnings, and then we took that same thing in the GPU. So implemented the same interface and specification on the GPU, and then now, so I think we covered this one already. So now as I said, we implemented on the FPGA, and we had some learnings, and also there are it's a little bit different than coding an unconventional way of implementing things in GPU. So we took the PDU specification and implemented on the GPU, and we published some numbers compared to CUDF. So it's almost more than half a year old. So I'm going to skip this for now. So in the interest of time, so now these are some numbers where we ran, as John mentioned, DPS is our product. So we took the Spark, and then this is a general customer setup that most of our customers use, which is a DataPelago Spark implementation with 2 of those high mem nodes with 1 NVIDIA Tesla TPU each, T4 GPU each. And you might know the available memory is only 16 gigs, so two of those total is 32 gigs. So there's a lot of invention in innovative things in how you manage that, when do you evict asynchronous memory allocation and asynchronous things like that. So our data, most of our customers store their data on the cloud storage, Google or S3. And then in this talk, I'll just pick 2 queries, one from each, TPC-DS and TPC-H. And then the actual performance number doesn't matter because it changes on the cluster configuration. So we normalized everything to 100 seconds, and GPU utilization is mostly 100%. So on the left-hand side, what you see is the typical Spark plan, and the Velox column shows how much time, normalized to 100 seconds, how much time the Velox operator is taking. And this exact same operator, the last column shows how much time the same operator is taking on the data VM implemented on a GPU. Now, there are two main reasons why you see that gain. One is as I said, our data is on GCS, so we made some improvements there in the scan part, and also these are all Parquet files, so it's a Parquet decode part. And GPUs are really good at faster filtering part, so that's where you gain the filter part of it. And the second one is this TPC-H, one more from the TPC-H test suite. Here, this particular query is more heavy on the projects and aggregates. So you can see the project time is almost 56 seconds to 1 second, and then the filter plus scan part is 46 to 40 seconds. You see around 5x gain here. So that concludes. Thank you.
So that was, I guess, a quick view of how DataPelago Nucleus works on some example TPC-DS. Our customers obviously are not running TPC-DS. I think everyone knows that. So when they are running some arbitrary workload, a common question that the customer faces is, well, what is this going to do for my workload? How much is it going to accelerate? It's a hard question to answer, as everyone who has experience knows. Acceleration depends on a number of things: what operators are part of the plan, what kind of data is being processed, what are the characteristics of the data, and then the acceleration engine itself, what does it involve? What are the fixed costs associated with the engine? What are the data conversions that are involved, and other kind of attributes? And then, if you know people who use Gluten and Velox know there is this fallback, unsupported operators fallback. So it's basically a mixture of engines that are being deployed. So some of them are executing in one or the other. So it's about what are the overheads associated with those engine fallbacks and things like that. So this simple way to deal with this thing is, you just say, if the operator is supported, run it on the accelerator engine. Otherwise, you fall back. That's kind of the default Spark, Gluten, Velox approach. You could try something a little bit more, saying, hey, I want to optimize or minimize the overheads. So I'm going to now say if the stage supports all operators that are supported, then I'm going to execute that stage in the accelerator engine. Otherwise, I'm going to just run that stage in the Spark engine to basically hide the transition costs with the exchange and so forth. Or you can try to be a little bit more intelligent, say I'm going to assign some cost for the operator, and I'm going to include some high cost for the conversions and things like that. Those are all what we have found are quite simplistic. As you can see in the chart there, all the greens are supposed to be running in the accelerated Velox engine. The blue ones run on Spark, and then all the yellow things are all the transitions that go back and forth. So when you do these kinds of things, what we have found, I think people who have experience in the field also know this, is we are then delegating the burden to the user or the customer itself. What is the burden? First, the application itself may degrade because you are moving things back and forth, you can degrade. And if they want to avoid this degradation, they have to go through the burden of actually testing the workload, tuning the workload, configuring the workload. It's something that you can do for 10, 20, 50, 100 workloads, but if a customer has 1,000, 10,000 kind of workload, this becomes impossible task, right? So this is the problem. So what we built for that is something called smart acceleration. The basic idea is we want to optimize the performance of the workload by targeting the acceleration dynamically, not by configuration, upfront configuration, by targeting the acceleration dynamically based on runtime information. When you say targeting acceleration, it is about saying what is going to run on, if you have a mixture of engines, what is going to run on which engine, right, and how. So this dynamic engine includes decisions based on workload independent aspects. Is there a GPU here or not? And what is the speed up that I expect on my engine? Is the operator supported or not? And then there are things that are workload specific as well. What is the sequence of operators? What happens after this supported operator? and what are the characteristics of the data, what data types, how much data, and so forth. And we want to do this without requiring any configuration from the customer itself, from the user itself. So that's what smart acceleration does. Basically, there is a mechanism, and then there's a policy. The policy itself is based on a cost model. The cost model, at a broad level, it factors data related information. As you can imagine, shape of data, types of data, volume of data, and things like that. Statistics related with the data. Complexity of the operator and the data types, whether you have complex types or it's just scalar types. And then some characteristics of the engine. You need to know how your engine, what works, where it performs better, and what are the fixed costs, and so forth. So we have a model structure describing this cost model that we have built through studying our own system with a variety of workloads. And then that's a parameterized cost model, and we retrieve the parameters based on the runtime information itself. So that's the policy part of it. And the mechanism itself, in the context of Spark, it still uses the Spark plan. It captures the logical and the physical plans that are emitted by Spark. It also retrieves the statistics that Spark retrieves when it's available. We basically use those things to infer, because we may do more sophisticated filtering, so the data statistics change as you go up the plan. So we infer those kinds of statistics, and then we generate alternative plans, and then pick the one that is the most optimal using that cost model. So that's basically what we have. Here are some illustrative examples. Obviously, we do this for customer workload, but those workloads are all pages long. So we're trying to kind of illustrate the point here. So here, basically, it's a Spark environment. For this case, we are only using CPU because we want to compare it with off-the-shelf Gluten and Velox. The data set itself is a SF1000 TPC-DS data set living in cloud storage. These are all synthetic query. So in this case, you can see this specific query ran for 25 seconds in vanilla Spark. And Gluten takes a longer time. It runs in 52 seconds. The interesting thing is that for this specific query, all operators are supported by Gluten. There's really no fallback. So if you had a policy saying, if there is no fallback, I will just run the workload, you would be degrading your performance. So your workload will actually perform worse, even though there's no fallback. Now, with the smart acceleration, we are able to find out characteristics of the data and the operators and make runtime decisions to choose the right plan for executing. And with that, we actually perform better than both Spark and Gluten Velox at 24 seconds, right? So that's one example. The other example, this is the last slide, yeah. The another example is similar, but here you can see that Gluten and Velox actually speeds up the performance, but we can actually perform even better than that. And in this case, there is actually a fallback because of the in-memory table scan. We don't enable the table cache flag. So even though there is fallback, Gluten and Velox performs better. But we actually perform even better than that. Anyway, so this gives you an illustration that just using simplistic fallback-based decision to run it in Spark or run it in Gluten and Velox is not going to get you what you want, which is acceleration. And smart acceleration is kind of an interesting way to kind of address this problem and make sure that you don't degrade applications and you actually improve them as much as possible. Anyway, thanks. That's basically what it is. So everyone has talked about composable architecture. Basically, Nucleus is that. It allows you to run diverse programming models, Spark, Plan, Trino, and things like that on CPU, GPU, and other kinds of infrastructure. We talked about Data VM, which is basically a platform for hybrid CPU-GPU acceleration, and then how smart acceleration can allow you to accelerate performance, and more importantly, do it in a way that customers can actually now widely deploy this platform for a large number of workloads without having to do manual tuning on this. Thank you very much. Yeah.